A creek 2 feet wide stopped the Transcontinental Railroad for months, a shallow stream at the bottom of a 150-foot gorge, and the question of how to get a locomotive across it. The answer took an entire winter to build, and it terrified everyone who crossed it. On April 23, 1868, when the first train crossed the Dale Creek Bridge in Wyoming at 4 miles per hour, nobody was certain that it would hold. When the Union Pacific Railroad's construction crews reached the Laramie Mountains of southeastern Wyoming Territory in winter of 1867, they had already crossed the Nebraska plains and blasted through granite ridges approaching Sherman's Summit, the highest point on the transcontinental line at 8,247 feet above sea level. 3 miles beyond that summit, the ground opened into a narrow canyon. Dale Creek, barely 2 feet wide at its floor, had cut a gorge roughly 150 feet deep through the rock. Steam locomotives could not handle steep grades. Any detour through the mountains would have made the route commercially useless. General Grenville Dodge, the Union Pacific's chief engineer, made the call. The line would cross Dale Creek directly. The question was not whether to build the bridge, but how to build it across 650 feet of open air, at altitude, in winter, on schedule. Dodge had spent the Civil War building and destroying railroad infrastructure across the American South. He understood how quickly wooden structures could be raised, and how quickly they could collapse. By 1868, he was directing thousands of workers across hundreds of miles of open territory simultaneously. When Dodge looked at Dale Creek, he saw a calculation. Timber would come from Michigan, pre-cut in Chicago, and shipped by rail to the site. The structure would use the Howe truss, a design combining wooden beams with adjustable iron rods, allowing workers to compensate for the natural shrinking of unseasoned wood over time. It did not need to be permanent. It needed to carry trains westward before the year was out. Construction began in December 1867. The first obstacle was not the canyon, it was the rock on either side. On both the eastern and western approaches, workers cut through nearly a mile of granite using hand tools and blasting powder. Once the approaches were clear, crews established stone masonry piers at the base of the gorge. These foundations supported the vertical timber bents, the A-frame structures that formed the bridge's legs. Each bent rose in stages, one frame stacked atop the next, braced laterally against the Wyoming wind. The timber arrived green. Unseasoned wood was all the schedule permitted. This was not a mistake. It was a calculated trade-off, one the Howe truss was specifically engineered to handle. The Howe truss placed wooden beams, carrying compression, alongside vertical iron rods in tension. As the wood dried and shrank, those rods could be tightened with a wrench. The structure could be adjusted. But tolerances during construction were unforgiving. If a bent was raised even slightly out of plumb, the lateral load shifted unevenly across the entire frame. In a canyon with sustained Wyoming winds, strong enough to push empty boxcars off the rails, an out-of-plumb frame was not a minor problem. It was a failure waiting for the right gust. Workers balanced on rising timber without safety equipment in winter temperatures, tightening connections by hand. When the first train crossed and the bridge shifted under the weight, carpenters rushed onto the structure to shore up the movement. 2 of them fell to their deaths. The locomotive moved onto the bridge at 4 miles per hour. The structure swayed, not catastrophically, but visibly. Passengers gripped their seats. Some engineers, it was later reported, refused to stay in the cab during the crossing. A traveller who made the journey in 1873 wrote that fear came not from the bridge's appearance alone, but from the wind, so fierce, she wrote, that she prayed it would ease before the cars reached the centre span. It held. The train crossed. Within days, the crews were already 100 miles further into Utah territory. Dale Creek was not the only canyon. Across Wyoming, Utah, Nevada, and the Sierra Nevada, the Transcontinental Railroad demanded dozens of similar structures, each adapted to its terrain and load. Some bridges curved through mountain terrain, Some stood over 200 feet above valley floors. Each represented the same calculation: build fast, build with available materials, build well enough to generate revenue, then replace it when something better becomes possible. The Howe Truss made this possible at scale. It was not the most elegant solution, it was the only practical one. By the late 1870s, only a small number of bridge carpenters in the West still understood the full geometry of a large trestle. The knowledge was not in engineering manuals. It lived in the hands of men who had built them under contract and under deadline. When fire damaged the wooden approach span at Dale Creek in 1884, it had to be reconstructed from photographs. The Transcontinental Railroad was a political commitment as much as an engineering project. Dale Creek Bridge was proof, delivered on schedule, at altitude in winter, that the Union Pacific could fulfill its contract. The bridge appeared in Harper's Weekly in 1868. The workers who built it did not. They were largely Irish immigrants, Civil War veterans, and labourers from eastern cities. Many deaths during construction across the line were never formally documented. By the end of the 19th century, iron and then steel displaced wood for major railroad crossings. The transition was not driven by the failure of wooden bridges. It was driven by the growth of the trains themselves. Heavier locomotives and higher speeds pushed timber beyond its structural limits. The Dale Creek wooden trestle was replaced by an iron bridge in 1876, built on the original 1868 stone piers. In 1901, when the Union Pacific rerouted the line, the crossing was abandoned and dismantled. The stone foundations were added to the National Register of Historic Places in 1986. The first train crossed Dale Creek because Dodge made a decision that the railroad could not wait for better materials or better weather. Long before standardized steel or computer modeling, the safety of a structure across a 150-foot canyon depended on the accumulated judgment of men who understood how green timber moved, how iron rods responded to tension, and how Wyoming wind behaved in December. Dale Creek Bridge was never meant to last. It was meant to be good enough, fast enough, to keep a continent connected long enough for something better to follow. That calculation, precision in service of urgency, shaped the railroad network that shaped the American West. These structures shaped the country quietly, one canyon at a time. If you'd like to see more of them documented, consider subscribing, and tell us, which forgotten piece of engineering should we uncover next?